We're now going to go through and look at reactions that make alcohols. Some of these are going to be review, while others, particularly toward the end of this section, will be new. The first one we're going to look at is nucleophilic substitution reaction, essentially one of the very first reactions that we studied. Our observed reaction for this looks like this. We take an alkyl halide or some similar molecule that has a leaving group directly attached to an alkane type carbon. We treat it with an oxygen nucleophile. That oxygen nucleophile could either be a hydroxide, strong nucleophile, or water, weak nucleophile. At the end of the reaction, the leaving group has been replaced by an OH, thus synthesizing an alcohol. As I discussed earlier in the nucleophilic substitution reaction chapter, the nucleophilic substitution reaction is a very generalized reaction where there's a lot of different possible reagents we could put over the arrow. The different reagents then result in different specific products. We can use hydroxide. When we discussed nucleophilic reactions, we talked about that hydroxide would be a strong nucleophile, which would really favor SN2 reaction. However, it would have the limitation that SN2 reaction is only efficient on methyl and primary, and maybe in some cases secondary if we adjust solvents or things like that. You cannot do SN2 reaction on tertiary carbon groups. So that would limit the identity of the carbon group that we could have there. We also saw that SN2 reaction is a stereospecific reaction, and we specifically get inversion of configuration with that, which can have significance when we are working with chirality centers. In contrast, we can use a weak nucleophile like water. That is going to react by an SN1 reaction. In that case, we're going to want to use a substrate that will form a relatively stable carbocation. So we're going to prefer to use a secondary or tertiary substrate. The one caveat is that we would expect to see rearrangement in the case of using a secondary substrate that could rearrange to become more stable. At the end, although the water did attach as a nucleophile completely, it would be deprotonated so that at the end we would still have only one of the hydrogens and the oxygen attached. The other thing we would observe is that this is not a stereospecific reaction. In fact, we just get essentially a random mixture of both configurations at the chirality center, which we call racemization. We're next going to look at hydration reactions of alkenes, which we studied in Chapter 8. This again is a review. There were 3 hydration reactions that we looked at. They all had similar reactants and similar products. They used different reagents over the arrow, and they had different regiochemical and also rearrangement outcomes. The first was in some ways the simplest. We would just use dilute H2SO4. This is acid adding water into the molecule, so we called this acid catalyzed hydration. The dilute H2SO4 reagent is really a mixture mostly of water with a small amount of catalytic amount of H2SO4 sulfuric acid to speed up and facilitate the reaction. We saw that this reaction proceeded with Markovnikov regiochemistry and that rearrangements were common since we had a carbocation intermediate. The next review reaction is the oxymercuration demercuration reaction. This reaction started with an alkene again. It was a 2-step reaction where in the first reaction we would use mercury 2 acetate with water as a nucleophile, followed by treating with sodium borohydride to remove mercury from our intermediate product. Again, we end up adding a hydrogen and a hydroxyl group, effectively adding a molecule of water into the molecule. This reaction proceeded with Markovnikov regiochemistry, but there was never a free carbocation in this mechanism, so there would be no rearrangement. So it was complementary to the first reaction. You should go back and review this reaction because we are going to be using it as the basis for a reaction in a future chapter. The third reaction that we looked at as a hydration was called hydroboration oxidation. We start with an alkene. We use borane THF complex, BH3, complexed with THF. That's the first step. After we're done with that step, we would add in hydrogen peroxide and sodium hydroxide. At the end of this reaction, we would again have a hydrogen attached to one carbon of the former alkene and a hydroxyl group attached to the other carbon. So this results in the molecule essentially absorbing a molecule of water. The important thing about this was that this proceeded with the opposite regiochemistry, anti-Markovnikov. And again, there was no free carbocation, so we would not have rearrangement. These reactions were covered in great detail in Chapter 8, and I highly recommend that you go back and review that for more information. We are now going to look at a new reaction that creates an alcohol from a ketone or an aldehyde. There's actually two observed reactions because we have two very similar reagents. We'll discuss the difference between them down below. But the overall reaction looks like this. We start with a ketone or aldehyde, which has a carbonyl, a C double bond O, attached to a hydrogen or carbon on one side and a hydrogen or carbon on the other side. We treat it with this reagent or this reagent. This reagent is called sodium borohydride. The formula abbreviation would be NaBH4. This reagent is called lithium aluminum hydride, LiAlH4, sometimes abbreviated LAH. This reagent produces a hydrogen minus, we're going to see. The hydrogen makes a bond to this carbon and pushes one of these carbon-oxygen bonds out of the way. So that at the end, what we have is we have an additional hydrogen attached to our central carbon, and we have a hydroxyl group here instead of a carbonyl. We've reduced the number of bonds to this oxygen heteroatom. So this is called a reduction. And often this reaction is called hydride reduction. Looking at the mechanism, I first want to start with explaining these hydride reagents. These hydride reagents are essentially sources of something that behaves like hydride ion. Hydride ion, over here, would be a hydrogen with 2 electrons on it by itself. If we calculate the formal charge of that, the hydrogen would want 1 electron, it would own 2, so 1 minus 2 is -1. It would have a -1 charge. It's called hydride because the IDE ending is commonly used for monoatomic negative ions. So in this case then, we have a hydrogen monoatomic negative ion, we call it hydride. Hydrogen is going to be a strong base, hydride, is going to be a strong base, and also a nucleophilic hydrogen. Now, the way that this actually works is the boron and the aluminum have very low electronegativities, boron has an electronegativity generally given in the range of about 1.9. Aluminum is even lower at 1.6. Hydrogen electronegativity is usually given somewhere in the range of about 2.1. If we draw a bond polarity arrow then from the central atom boron or aluminum to one of the attached hydrogens, we see that that arrow points in the opposite direction from what we might normally see. The arrow points toward the hydrogen, which means that hydrogen is going to get a partial negative charge. And the central ion would prefer to have kind of a partial positive charge. Increasing the effect then is going to be the fact that by making 4 bonds to a central boron or 4 bonds to a central aluminum, they are going to end up with a negative charge. They're going to have an excess of electrons. Boron, for example, and aluminum want 3 electrons. In this configuration, they own 4 electrons. They get a negative charge. The overall sodium borohydride and lithium aluminum hydride then is actually an ionic substance composed of a sodium or lithium positive ion and a borohydride or aluminum hydride negative ion. And it's that negative borohydride or aluminum hydride ion that is the reactant. We also see, if we look at it this way, that lithium aluminum hydride is going to be more reactive than sodium borohydride. The reason for that is that the electronegativity of aluminum is lower than that of boron, which means that this arrow is going to be even longer, even more strongly pushing electrons out, and the electron density on the hydrogens of aluminum hydride is going to be higher than the electron density of the hydrogens on borohydride, making them more reactive. I should point out that there was a typo, which I've corrected right here. We're now going to look at the mechanism of this. Now, I do want to point out that the mechanism that I am going to present is what's called a formal mechanism, in that it is a mechanism that is totally consistent with our rules for moving electrons and drawing structures. However, it might not be the exact real mechanism in the sense that there may be different species or different atom movements that are accomplishing effectively the same thing. In this case, for example, we're going to draw a hydride ion as our reactant. In reality, we probably never have a hydride ion floating around in the solution by itself. That's a pretty high energy species, and the bond between borohydride hydrogens or aluminum hydride hydrogens, those bonds are very polar but still covalent. Nevertheless, that very polar covalent bond acts as if it were a hydrogen ion by itself nucleophile, and once we draw that species, it becomes pretty understandable how you could use this pair of electrons to move down and make a bond to the carbon atom of the carbonyl, because the carbon atom of the carbonyl itself has a partial positive charge because it's attached to an electronegative oxygen. So it has a bond polarity arrow. So we have this negative charge attracted to that partial positive charge. Now we can't just draw a bond there because that would make 5 bonds to that carbon. Carbon being a second row atom will not have an expanded octet, so therefore we are going to move one of these bonds of the double bond out of the way, pushing it out onto the oxygen and creating an oxygen with 3 lone pairs and a negative charge. If we make a bond here then, using the blue pair of electrons, and we move this pair of electrons out there, this is the species that we get. This is an alkoxide. It has a negatively charged oxygen. We would expect that the counter ion or even the boron or aluminum itself might become attached there. After that occurs, we need to put a hydrogen onto that negative oxygen to make an alcohol. The source for that hydrogen depends on which reagent we're using. In sodium borohydride, we mix the sodium borohydride reagent directly with methanol as a solvent, directly with our ketone. So once this is formed from our reactant, there are solvent molecules available that can be deprotonated by the alkoxide, forming our final product. We cannot mix lithium aluminum hydride directly with alcohols. It's too reactive, and we get an almost explosive exothermic reaction, which in fact, with smaller alcohols, will actually create flames in the reaction vessel as the hydrogen that's released reacts with oxygen in the container and essentially combusts. Therefore, what we have to do is complete our reaction for the first part with lithium aluminum hydride, and then very carefully add in an acid or an alcohol to allow reaction. Generally, we use strong acid in water, aqueous strong acid, which organic chemists like to represent as hydronium ion. The hydronium ion would then be the acid. It would get deprotonated. We would create a molecule of water just in the larger molecules of water in the solvent. Again, that would put a hydrogen here, creating our alcohol final product. One of the consequences of lithium aluminum hydride being more reactive than sodium borohydride is that lithium aluminum hydride will react with higher oxidation state carbonyl substances like esters and carboxylic acids, and we're going to say later even amides, although the outcome is dramatically different. For esters and carboxylic acids, what we see is that if we use an excess of lithium aluminum hydride followed by aqueous hydrolysis, what we would see is we would add two hydrogens here, the OR prime, the alkoxide group of the ester, or even the hydroxide group of the alcohol would be removed and also replaced with a hydrogen. And essentially, we take this down two oxidation states all the way down to an alcohol. So our product is an alcohol product. We're not going to talk about the mechanism of these reactions. They start the same as the hydride reduction of ketones, but then they go in a different direction. So later on this semester, we'll talk a little bit about that.